Okay, in this section we're going to look at finding the volume of a solid of revolution using the disk method. So the definite integral can be used to accomplish this if we are setting it up correctly. So let's talk about what a solid of revolution is. When a region in the plane is resolved around a line, the resulting solid is called a solid of revolution. The line itself that's being revolved around is called the axis of revolution. And the simplest such solid is a right circular cylinder, or a disk, which you can form by revolving a rectangle about an axis adjacent to one side of the rectangle. Now the volume of this disk is going to be the area of the disk times the width of the disk, which would be pi times r squared times w, where r is the radius and w is the width. So if this is my rectangle and I'm going to revolve it around this axis, my radius of the disk is going to be this capital R distance here, the y on this graph, and my width is going to be the width of the rectangle, or the change in x, delta x. And if we describe the rectangle above, we're going to generate a disk whose volume is v equals pi r squared times delta x. So this is the basis of the disk method, and you can see that what we're doing is we're taking a solid and we're chopping it up into these little disks that kind of approximate the volume of this solid. So each individual disk we're going to calculate the volume of and approximate that, or add those together to approximate the value of this. Now, of course, to actually get a really close representation of the volume, it would be better to have infinitely many disks. So instead of thinking of, all these jointed rectangles on our region here, we're going to think of the pattern for our solid, the thing that's being revolved, as having infinitely many rectangles inside it, which is going to form infinitely many disks in the solid. So it will give us a really good estimation of what the volume is of this blue solid here. So the volume of a solid estimated within disks is going to be the sum from 1 to n of pi times r of x of I squared, that's the pi r squared, times delta x. And if we want infinitely many disks, we're going to use a limit or an integral, preferably an integral. So we know the volume of one disk. We have our representative element as delta v equals the volume of the ith disk. Okay, and our integration formula then is going to be pi times the integral from a to b of r of x squared dx. So we're taking the kind of differential form, and we're converting, or we're taking these differentials and converting them to this solid of revolution volume formula. So you can see where the pi comes from, you can see where the r of x squared comes from, and then you know that dx and delta x are approximately the same. So this is the disk method. If you want to find the volume of a solid of revolution, you're going to use one of the two formulas below. If you happen to have a horizontal axis of revolution, you would want to use the x version of it. And if you happen to have a vertical axis of revolution, you want to use the y version of it. So you can see graphically what those two look like. This is the same exact shape. The blue shape is the same. In this case, we are revolving it around the x-axis, and you can see the shape that would kind of make there. And in this case, you're revolving it around the y-axis. So if that's the case, you would calculate your r of x in the left-hand side to be the height of the rectangle that's formed vertically. And in this case, you would calculate r of y to be the width of the rectangle that's horizontal. So it's the length, but it's the distance from here to here. So let's do an example. It says, find the volume of the solid formed by revolving the graph of f of x equals negative 3x plus 6 and the x-axis from 0 to 2 about the x-axis. So we do have a horizontal axis of revolution. Those are the easier ones, so that's a good thing. And we have the graph of y equals negative 3x plus 6 here. and we're only looking between 0 and 2, so we're basically finding the volume of revolving this triangle about the x-axis, and you can see that that's going to form this nice pretty cone shape. So because I have a horizontal axis, I want vertical rectangles. So I'm going to come in here and just drop a rectangle and kind of think about what that would look like. So this would be an example of a rectangle. I am going to delete this shading here so you can see it a little clearer. So the height of this rectangle, r of x of I, is basically whatever the function height is at x of I. So my r of x is just going to be the function negative 3x plus 6. So my bounds, of course, are going to be from 0 to 2. So I'm going to have pi times the integral from a to b of r of x squared with respect to x, whatever the function is, squared. And in this case, that's going to be the integral from 0 to 2 of negative 3x plus 6 squared dx. Now you have some options when you're integrating these. You may have to use the chain rule when you're squaring this. In this case, you could FOIL this out and integrate directly. It's up to you. I'm going to use the chain rule, so I'll let u be negative 3x plus 6, which means u prime will be negative 3. So I would need a negative 3 on the inside of the function and on the outside of the integral. So now I'm taking the integral from x equals 0 to x equals 2 of u squared du, which we know is u cubed over 3. And I get negative pi over 9. U was negative 3x plus 6 cubed, and that goes from 0 to 2. So now I'm just going to plug in my bounds. And the first one will have negative 3 times 2 plus 6 cubed, and the second one will have negative 3 times 0 plus 6 cubed. Be careful with stuff like this because plugging in a 0 doesn't actually give you a 0 outcome here. Oddly enough, plugging in the 2 does. So this is actually 0 cubed minus 6 cubed, all times negative pi over 9. And negative 6 cubed is times the negative pi over 9 is going to give us 24 pi units cubed. Now we are in units cubed because this is volume. Another thing to notice is that I'm not actually multiplying it by pi and getting a decimal approximation. You only want to do that if you are told to give a decimal approximation. Another thing I want to point out, there's kind of two parts to this. There's setting up the integral and there's evaluating the integral. So when you're showing your work on a test, I want to see you actually evaluate this integral. If you put it in the calculator and give me a decimal answer, you will not get full credit for this. I want to see you actually evaluate this integral. Okay, when we look at this one, it says we're revolving the region bounded by the graph of f of x equals 4 minus x squared. The x-axis from 0 to 2, about the x-axis. So we're looking at this region here, and we're going from 0 to 2, and we are revolving it around that horizontal axis of revolution. So we are still in the x version of this integral. So my rectangles will be vertical, and you can see that r of x is just going to be the function 4 minus x squared. So my v is going to be pi times the integral from a to b of r of x squared with respect to x. And that's going to be the integral from 0 to 2. And r of x is 4 minus x squared dx, and then that's all times pi. Now with this one, I don't have the x I would need for my u prime because u prime would be negative 2x. So I do need to actually FOIL this out. So I will do that and I'll get 16 minus 8x squared plus x to the 4th if I FOIL that out. And then I'm going to integrate. So I will have 16x minus 8/3 x cubed plus 1/5 x to the 5th. And that's all from 0 to 2 and multiplied by pi. So when I plug in the 2, I'll have 16 times 2 minus 8/3 times 2 cubed plus 1/5 times 2 to the 5th. And then when we plug in everything else, we'll have 16 times 0 minus 8/3 times 0 cubed plus 1/5 times 0 to the 5th. You can see that that second part all goes to 0. So I have 32 minus 64/3 pi plus 32/5. So that gives me, or sorry, minus 64/3 plus 32/5. Haven't put the pi in there yet. So that all gives me 256 over 15 pi units cubed. And unless you're told otherwise, leave that in that exact value. Okay. Now this one is formed by revolving the region bounded by the graphs of f of x equals 5 minus x, x equals 0, and y equals 0 about the y-axis. So in this case, we were revolving around that vertical axis, and we're going from x equals 0 to y equals 0. So the region is this entire triangle here. Okay, so if you need to see the region, that is the region. And since we have a vertical axis, we're going to form horizontal rectangles. So the rectangles are going to go like this. And we're going to be looking at r of y, which is going to be that distance there. Now it happens to be solved for y right now. Y equals 5 minus x. But I actually want to solve this for x and get r of y. So here I would start by adding x to both sides. So x plus y equals 5. And then if I subtract the y, I get x equals 5 minus y. So that's going to be my r of y. It is not always going to be just as simple as replacing the x with y, so do be careful with that. In this case it happens, but that's only because it's that nice linear in that format. Okay, we also need to know bounds, and the bounds in this case are going to be y values. So from our shape that we had before, which was here, you could see that the lower bound is going to be 0 and the upper bound is going to be 5. So we're going to be integrating. V is going to be pi times integral from c to d of r of y squared dy. So we're going to have pi times integral from 0 to 5 of 5 minus y squared dy. So again, it's up to you how you want to integrate this. I'm going to go ahead and FOIL it out first. So I'll have 25 minus 10y plus y squared. And when I integrate that, I get 25y minus 5y squared plus 1/3 y cubed from 0 to 5. And I'll plug these things in. So I'll have 25 times 5 minus 5 times 5 squared plus 1/3 times 5 cubed. And then when I plug everything else in, you can see you get a 0. So this is pi times 125 minus 125 plus, and I forgot to plug in the 5 here. Sorry, guys. Plus 125 over 3 minus 0. And I end up with 125 pi over 3 units cubed. And that will be my answer.